This is Angel. This is the original process. This is part C of the project. The original process of finding the proton's mass began after Rutherford discovered the proton in 1917. Early scientists used mass spectrometers to measure how hydrogen ions moved in magnetic and electric fields, allowing them to compare their mass to other atoms. This showed that the proton's mass is about 1 AMU over time. More precise tools confirmed this value, and modern physics revealed that most of the proton's mass actually comes from the energy inside, not just its particles. The original difficulties: there was limited technology, separating particles was also another difficulty. The unknown atomic structure was another difficulty. Measurements of charge to mass ratio, energy versus mass, and confusion. The original motivation for finding the proton's mass came from scientists' desire to understand the structure of the atom. After discovering the electron, researchers like Ernst Rutherford wanted to know what made up the rest of the atom and how much each part weighed. Measuring the proton's mass helped confirm that it was a major component of the nucleus and gave clues about how atoms differ from one another. It was also an important step towards developing the atomic model and understanding the forces inside of the atom. The original benefits were better atomic models, identification of elements, foundation of chemistry and physics, advancement of technology, and a step toward nuclear energy. The modern process was the pinning trap method, which is when protons are trapped using strong magnetic and electric fields in a device called a pinning trap. This keeps the proton suspension in place without touching anything. The cyclotronic frequency measurement, which is how scientists measure how fast the proton moves and the magnetic field. Comparison with other particles. That's the proton's mass is compared very precisely with the mass of other well known particles. And quantum corrections, which is how physicists use quantum electrodynamics and other modern theories to correct for tiny effects that can influence the measurement. The modern differences is the technology. We are more advanced right now than we were before. The accuracy, we are way more accurate thanks to advanced electronics and computer analysis. We understand it better. Originally, scientists didn't know why the proton had its mass. Now we know most of it comes from energy inside the proton. Methods: early experience measured how particles bend in magnetic fields. Modern ones measure frequency, energy levels, and quantum effects. Purpose: the original goal was to understand atomic structure. Today, the focus includes testing fund, exploring how mass is created in the universe. The modern benefits is improved scientific accuracy, way more accurate, better understanding of matter, knowing how the proton's mass comes from energy inside it, deepens our understanding of how matter and the universe works, advances in technology, testing theories in physics, accurate proton mass data helps scientists test and refine modern theories like quantum chromodynamics. Applications in other fields. Exact proton mass values are important for nuclear energy, medical imaging, and space exploration. Future expectations: even greater precision. Scientists aim to measure the proton's mass with even smaller error margins. Understanding mass origin. Future research hopes to fully explain how mass is created from the energy of quarks and gluons inside the proton. Discovering new physics. Tiny differences in proton mass could reveal new particles or forces beyond what current physics explain. Improved technology and application in space and medicine. More precise knowledge of atomic masses can improve space navigation, radiation therapy, and other advanced technologies. And that is it. Thank you for watching.